Science. And with me is Dr. Mary Garson from the University of Queensland in Brisbane, Australia. We are thrilled to welcome you to the 2021 Iupac Global Women's Breakfast.
Good day from Brisbane in Australia. It's our very great honour to kick off the 2021 Global Women's Breakfast, Empowering Diversity in Science. We know many of you were there with us back in 2011 when we hosted the very first Global Women's Breakfast. Thank you. And also welcome back to those who participated in 2019 and 2020.
This year, we want to extend a special welcome and thank you to the organizers, the men and women who have stepped forward in their organizations, and also to those who are attending the Global Breakfast for the very first time.
We love seeing all types of organizations participating. That includes universities, scientific societies, industry, the government sector, and most importantly, high school classes of aspiring scientists. And there's always so much excitement. The very first breakfast starts in New Zealand, of course, and on the global map on our website, from that moment on, we see a sea of red hearts lighting up as breakfasts start around the globe.
It's really your leadership and enthusiasm that has inspired Iupac to make this an annual event. If we look back at the previous breakfast, chemists from all over the world, from more than 50 countries, joined in. In both 2011 and 2019, we were really celebrating, and rightly so, the achievements of women chemists. In 2020, we started developing a true global network, and now this year, we're ready to put it into action.
So today we're asking groups to connect with each other, to strengthen the bonds that have already been created, and to extend those networks to include new groups and organisations. And this is so important in the current COVID-challenged world where many people have been feeling isolated.
That's right, Mary. And looking at the many groups who have developed programs for their events, some are highlighting, women leaders in their organizations, some are having conversations on the challenges that women face in their careers, and others are supporting young scientists in their organization. Really, networking is the key, and it's important for empowering chemists and the scientific community in general. We really need to encourage women at all different career levels to come together and support and mentor each other.
And so this leads naturally to excellent opportunities for young people, particularly women, to contribute to the work of their own professional societies and generally to the scientific and community work undertaken, of course, part of it by Iupac. So all of this, hopefully good quality coffee and baked goodies for breakfast as well. Let's now hear from our friends from around the globe who want to join in and celebrate with us the Iupac Global Women's Breakfast of 2021. Enjoy, everybody.
Salam sejahtera dan selamat datang ke Global Women Breakfast 2021 dari Malaysia.
Hello and welcome to the Global Women's Breakfast 2021 from Christchurch, New Zealand. Cheers!
สวัสดีค่ะสุภวรรณตันตยานนท์จากประเทศไทยยินดีต้อนรับเข้าสู่งาน The Global Women Breakfast 2021 ค่ะ
日本からこんにちはグローバル女性朝食会2021年へようこそ私たちもいただきます
大家好
欢迎大家来参加由 Singapore 主办的2021年
国际女性早餐会
Hola नमस्कार भारत से ग्लोबल वुमेन्स ब्रेकफास्ट 2021 में आपका स्वागत है
Всем привет от российских женщин-химиков из заснеженной России.
أهلا بكم وصباح الخير من مصر. أهلا بكم في الفطار الجماعي Global Women Breakfast.
Merhaba, Global Women Breakfast 2021'e hoş geldiniz. İstanbul, Türkiye'den bütün bilim kadınlarına sevgilerimle.
Madam is audible?
Global Women's Breakfast.
Yes, Sonia Mam joined actually.
Yes,
joined. Sonia Mam.
Hello, Global Women's Breakfast 2021 από την Ελλάδα.
Hallo und willkommen zum Global Women's Breakfast 2021 aus der Schweiz.
Buongiorno e benvenuti alla Global Women Breakfast edizione 2021 Empowering Diversity in Science che si terrà il 9 febbraio presso il Dipartimento di Farmacia dell'Università degli Studi Federico II.
Hello and welcome to the Global Women Breakfast 2021.
Bem-vindos ao Global Women's Breakfast 2021.
नहीं तो मुझे नहीं
Yes,
आ रही है तुमको आ रही है
yes, audible.
Don't go.
तुम किससे कर रही हो मोबाइल से कर रही हो
Welcome to the Global Women's Breakfast in Newfoundland, Canada.
Hola a todos, bienvenidos. Anímense, vamos a desayunar.
صباح الخير للجميع وين ما كنتوا اهلا وسهلا فيكم
इनको बोलो कि तुम नहीं लेना कोई प्रॉब्लम हो
Bom dia. Sejam bem-vindas
किसी और
ao Global Women Breakfast 2021 em São Paulo, Brasil.
Hola, bienvenidos al Desayuno Global de Mujeres 2021 en México.
करूंगी तो ये आवाज आने लगेगी
Welcome to Global Women's Breakfast at IPS Academy Indore.
Good morning, everyone. From St. Louis, USA, I'm Laura McConnell from Bayer Crop Science. And with me is Dr. Mary Garson from the University of Queensland in Brisbane, Australia. We are thrilled to welcome you to the 2021 Iupac Global Women's Breakfast.
Good day from Brisbane in Australia. It's our very great honour to kick off the 2021 Global Women's Breakfast, Empowering Diversity in Science. We know many of you were there with us back in 2011 when we hosted the very first Global Women's Breakfast. Thank you. And also welcome back to those who participated in 2019 and 2020.
This year, we want to extend a special welcome and thank you to the organizers, the men and women who have stepped forward in their organizations, and also to those who are attending the Global Breakfast for the very first time.
We love seeing all types of organizations participating. That includes universities, scientific societies, industry, the government sector, and most importantly, high school classes of aspiring scientists. And there's always so much.
Welcome to Global Women's Breakfast at IPS Academy Indore.
A very warm good afternoon to all dignitaries. Am I audible to all of you?
Yes, you are audible.
Our chief guest and our eminent professor also joined the meeting. Shall we start, ma'am?
Yes.
Okay.
Our chief guest, Mrs. Archana Chitnis, ma'am. Our eminent speaker, Professor Sonia Alexandra, ma'am, has joined the meeting. Shall we start the meeting, ma'am?
Yes, Pratima ma'am. Ma'am said yes.
Okay. A very warm good afternoon to all dignitaries. Honorable Chief Guest, Mrs. Archana Chitnis, ex-Cabinet Minister, Women and Child Development, Government of Madhya Pradesh. Respected Dr. Sonia Alexandra, ma'am, Professor and eminent speaker from Portugal. Principal, ma'am, all HODs, professors, young scientists, and my dear colleagues. On behalf of Department of Chemistry and organizer GWB 2021, I, Dr. Pratibha Sharma, delighted to offer a gracious welcome to all of you and feeling immense pride to stand here before you in inaugural ceremony of IUPAC Global Women's Breakfast. The function of prayer is not influence God, but rather to change the one who prays. Inviting all the dignitaries to join the Saraswati Vandana along with lighting of lamp. Thank you, Kalal sir, for creating an aura of e-prayer. On this auspicious occasion and ever delightful evening, I feel privileged to present a floral welcome and greet our Honorable Chief Guest, Srimati Archana Chitnis, ex-Cabinet Minister, Women and Child Development, Government of Madhya Pradesh. Welcome, ma'am. We are honored to have you as our guest. I feel fortunate to present a floral welcome to our respected guest and eminent speaker, Professor Sonia Alexandra from Portugal.
Thank you.
Thank you, ma'am, for joining us. To create the memory of this event, I request all the dignitaries and participants to please turn on your video for a group photo. This photo will be uploaded on IUPAC's website. I am requesting all the participants to please turn on your video for a group photograph. Honorable Chitnis ma'am, Dr. Sonia Mam, please turn on your videos, ma'am, please. Respected professors, dignitaries, please turn on your videos for a group photo. Kalal sir, have you taken the screenshot of this group photo? May I proceed further? Kalal sir and Solanki sir?
I think we should proceed, ma'am.
Yes, proceed, ma'am.
Okay, thank you. Now, before moving ahead towards the program, I would like to introduce today's event initiated by IUPAC with the theme Empowering Diversity in Science. I feel proud to be the part of this event and very happy to brief IUPAC and GWB among us. The International Union of Pure and Applied Chemistry is a globally recognized union of chemistry organizations. The vision of IUPAC is to be the indispensable worldwide resource for chemistry, to provide scientific expertise for the benefit of humankind. The main aim of celebrating GWP is to connect together young men and women chemists, sharing ideas and information with other groups, assist the global network of highlight progress in reducing the gender gap, and addressing issues such as encouraging more women chemists into senior or leadership roles. It also aims to encourage more women chemists to apply for national and regional awards in their sub-disciplines. In lieu of this, IUPAC has initiated the Distinguished Woman in Chemistry Awards program to acknowledge men and women to promote the work of women chemists worldwide. I also feel privileged and delighted to announce that Indian Association of Chemistry Teachers, Mumbai, has promoted this event at grand level, which resulted the maximum participation from India across the world. More than 53 events are organized today from India. Today, it gives us immense pleasure to celebrate this global event at IPS Academy and Jhabua campus jointly. IPS Academy, blessed with women educators and administrators. In reference to this, I would like to invite our motivator and principal, Dr. Premlata Gupta ma'am, to give welcome address to the gathering. Ma'am, Gupta ma'am.
Am I audible?
Yes, ma'am.
Today's chief guest, respected Srimati Archana Chitnis, ex-cabinet minister, women, child development and education, government of MP. Our invited speaker, Dr. Sonia Alexandra, professor, Department of Chemistry, Portugal. A very warm good afternoon to everyone who are gathered here for participation in international webinar on empowering diversity in science on occasion of IUPAC Global Women's Breakfast GWB 2021, which is organized by Department of Chemistry, Institute of Science and Research, IPS Academy, Indore, in collaboration with International Union of Pure and Applied Chemistry and Association of Chemistry Teachers, TIFR, Mumbai. Indore Professional Studies, that is IPS Academy, is one of the Central India's largest education hub premises, playing a major role to develop Indore as Central India's most preferred educational center. It is sprawled in an area of 60-acre lane. We house the most intellectual, experienced educational assembly. Institute of Science and Research offers many undergraduate and postgraduate courses with various combinations. GWB 2021 is initiated by IUPAC to encourage men and women to empower science globally. It is celebrated in large number in India. This program is popularized by Indian Association of Chemistry Teachers. In this series at IPSA, we are organizing this webinar on empowering diversity in science, in which about 350 participants, along with international participants from Nigeria, Indonesia, Kenya, Oman, have registered. On this occasion, I would like to emphasize we must ensure that women's participation in science and innovation is not the expectation but becomes the norms. The main aim of IUPAC to organize such event is to empower diversity in scientific world by motivating and encouraging women. I believe great decisions come from gathering, valuing diverse perspectives. There is a well-known saying in India, Yat Naryastu Pujyante Ramante Tatra Devta. Where women are worshipped, there the god rejoices. This is the core ideology of women, Indian mythology. Lastly, I conclude, the great scientist Madame Curie said, I was taught that the way of progress was neither swift nor easy, so women in all forms are ready to carry out tough task of scientific development innovation. Thank you very much.
Thank you, ma'am, for your influential words. Coming together is beginning. Keeping together is progress, and working together is success. Is what indeed this mantra of working together that has brought us where we are today. Inviting Mrs. Ruchi Srivastava, Head Department of Chemistry, to say a few words.
Thank you, Pratibha ma'am. A warm good afternoon to all. Eminent personalities present over here. I welcome you on behalf of Department of Chemistry, ISR IPS Academy Indore. It is a glorious moment to extend my warm wishes and heartfelt gratitude to Mrs. Archana Chitnis Mam, ex-Cabinet Minister, Women and Child Development and Education, Government of MP, and also Dr. Sonia Alexander Carabino from Portugal, for accepting our invitation and presiding over this webinar, for which we are getting an overwhelming response from USA, Nigeria, Indonesia, Kenya, and nationwide. It will be an opportune moment to refresh our empowering diversity in sciences. As since decade of research by scientists, psychologists, economists, they show that there are so many social diverse groups, diversity of gender, ethnicity, and races, which are more innovative than any other homogeneous group. So, scientists from all across the globe are celebrating this IUPAC Global Women Breakfast, and we, Department of Chemistry, accompanying this global event. Department of Chemistry. We are proud to announce that we are running 2 PG and 1 UG program. In the quest of academic excellence, we had made a great stride by capturing plus 25 merit positions, 4 gold medals in last 5 years. Along with this, a record and remarkable placements. Faculty members have excellent academic credential and involved in cutting-edge research in diverse fields of chemical sciences. We distinguish ourselves in many ways by imparting hands-on training on sophisticated instruments like HPLC, polarograph, flame photometer, and many more. By adopting green chemical methods in our chemistry lab, our students synthesizes commercial products in our labs by green chemicals and also provide training to rural areas. There is a student club that organizes various academic and non-academic activities, celebrating various days and events. The in-house projects, along with the project training, are greatly appreciated by students. We also recognized at national and international platforms by significant numbers of publications, government-funded research projects, number of MOUs, and also international awards in the name of faculty member. To exceed our vision towards the new approaches and techniques in technical discovery of chemical sciences, we have organized several workshops, conferences, intercollegiate competition, and today, of course, the international webinar. Once again, my heartfelt welcome to all respected dignitaries present over here. Thank you so much for joining this event. Thank you.
Thank you, Ruchi ma'am. If your actions inspire others to dream more, if your actions inspires others to dream more, learn more, do more, and become more, you are a leader. Ladies and gentlemen, on this note, we have with us a great personality and dignified leader, Mrs. Archana Chitnis ma'am, Honorable Chief Guest of GWB. Respected Madam, do not need any introduction. But still I want to emphasize on Madam's journey of achievement. Madam Chitnis is a leading politician and entrepreneur of Madhya Pradesh. Madam has been elected as a member of Legislative Assembly representing Burhanpur and had served as Education Minister and later Cabinet Minister of Women and Child Development in Government of Madhya Pradesh. She has keen interest in literature, spirituality, social services, and agriculture. A pioneer in the field of entrepreneurship of women, she had started Women Bank in 1998 to ensure the women participation for nation's progress. This bank is of the woman, for the woman, and by the woman. Madam opened new vistas of development and initiated innovative schemes and programs in her ministerial tenure, like rainwater harvesting, emphasize on greenery, Gaon Ki Beti, Ladli Lakshmi Yojana that aimed to uplift the girl child in society. It is my pleasure to request Honorable Chief Guest Ma'am to give blessings to the gathering and enlightening us. Welcome ma'am in IPS Academy.
Namaskar.
Namaskar ma'am, you are audible ma'am.
Fine, thank you. I'm really honored to be with this international level of women faculties in chemistry. And I'm especially grateful to Achal Chaudhary ji, President IPS Group of Institutions, Dr. Premlata Gupta ji, who is the principal of IPS Academy, Pratibha Sharma ji, and all heads of the department, professors, young scientists, national and international participants, Dr. Vijendra Singh ji. And while I was listening to you, in its own way, it's a miracle of technology that today we are connected to each other virtually, practically, although not physically. But at the same time, I would like to add to it a very old saying that science is a good servant but a bad master. And I was asked to talk on and put some light about women empowerment and some workplace issues, I think. That was it?
Gender equality at workplace, actually.
Okay, gender equality at workplace. I strongly believe that that world alone and that office alone and that home alone is a healthy and happy place where a woman can give her best. And I should say everybody can give one's best. As far as equality is concerned, it has to come naturally. But more than equality, I believe that complementarity is more important. We have a beautiful word in Hindi, which you translate in English like complementarity, that is paraspar purakta. We all alone are incomplete. And when we complement each other, that completes not only one person, but it completes all of them together. It may be two or more who complement each other. And the Indian ethos believes more in complementarity, purakta, and when you complement each other. I would like to go into some rational or scientific details about it. We say that every person is unique. When we say that every person is unique, and every person, if he or she is unique in his own or her own ways, I think equality stands nowhere before your uniqueness. And if all the time I'm conscious of it, that I am a man or I am a woman, that consciousness is not required all the time. If I am a research scholar, or say if I am a public representative, if I am an entrepreneur, whatsoever I am a human being. I am an expert or I am dedicated towards some mission in my life, or if I am responsible towards the society or towards the nation, towards the nature, towards the world as a whole, that responsibility gives me independence. I believe that the nearest synonymous word to independence is being responsible. The more you're responsible, the more you use your independence. And if all the time I am thinking of myself, that how XYZ may be my superior or my subordinate thinks about me, how he or she has behaved with me, if through and through I put all my mental energies focused on myself alone, I can neither be happy with myself nor I can make others comfortable or relaxed, or I should say a pleasantness in the atmosphere will not be there if I am all the time thinking about myself and expecting others to behave in such and such way because it pleases me. I am a strong believer of equality, but equality starts from respecting others' feelings, then naturally it's reciprocated to you. Today, we are heading towards a world in this particular time when I'm talking to you, today information technology and genetic engineering has come forward towards artificial intelligence. But artificial intelligence can have best of intelligence, but emotional intelligence and bonds amongst ourselves cannot be fulfilled by any artificial means. Being human makes you a person who is, I should say, meaningful to everybody around. The men and women to whom I'm talking to in this program at this moment are already enlightened and empowered people. And they have the torch of education in their hands. They are research scholars, and that too of chemistry, many of you. And many times we say that the chemistry of life, if the chemistry of life is good, rest all issues are taken care of. And what do we mean by chemistry of life? The chemistry of life, I believe, will be beautiful if bonds amongst us, between us, are strong enough. And one word which you in chemistry you, the professors and lecturers of chemistry, I think can understand better than what I do, is the word catalyst. Without a catalyzing agent, if everything possible is there, the reactions do not take place. And so I believe that all of us, in whatever positions of responsibility we are, we need to be a catalytic agent in every situation, that with our presence alone, what is required, what should be, what is noble, what is progressive, what is developing, can take place because of my presence. That's more important. We Indians, since ages, have been a society which is society with a duty-based society. The crux of our social fabric is duty, and when all of us are dutiful in our own selves, in a natural way, we take care of rights of other people also. Ironically, today we have become a generation that's concerned more about one's own rights than one's own duties. Recently, on 30th of January, we all remembered Gandhiji. And Gandhiji, in his times, have spoken it off very boldly and intelligently, that if the very principle of life is based on duties, it would be a better world. But if we are all only concerned of our own rights, I don't think only taking care of one's right can make you empowered, because duties and rights, it is the same, the two sides of the same coin, and it reciprocates. If one thing is taken care of, other reciprocates itself on its own. Straight is the line of duty. Straight is the line of duty. Curved is the line of beauty. Follow the straight line, you shall find the curved line follows thee. My dear friends, I don't know how much of time you people have given me. How long should I speak? But I only want to say you in short that alone we can do little, and together we can do a lot. As a woman, I believe that Almighty has empowered women beyond limits. But what a girl or a woman wants is equal opportunity. With any given opportunity, we can all work wonders. So what is required is the opportunity, and there is no force more powerful than a woman determined to rise. And when a woman rises, she doesn't rise alone. And when a woman rises, she rises with her family, with her surrounding. And she gives light to all around. as a homemaker, I believe, because being a political representative, a public representative or entrepreneur, I feel more honored and more important as I am a homemaker too at the same time. A mother never cooks for herself, but never sleeps hungry. If you look at the big picture of life, you can never feel low. You can never be a person with complaints. It is for us to decide whether we want to be a person with complaints or we want to be a person with solutions. Again, who better than a chemistry professor understands that the end result of everything has to be a good solution. In this diverse world, integration is very important. We can't think of this world in a compartmentalized way. We have to think of it holistically. We have to think of it in toto. And if you have a mission in life, if you have a goal in life, if you want to make your life meaningful, then an educational institute is the best place to make your life meaningful, in which we are I have also taught. I have been an assistant lecturer of zoology in Gujarati Science College in Indore for more than a couple of years. You are remembering me as a Women and Child Development Minister. I was looking after technical education too. I looked after women and child development, technical education, higher education, and animal husbandry also. My dear friends, I am remembering a small event which took place in Assembly of Madhya Pradesh. As a minister, I got up to speak on something. I was answering some question of an MLA. But the respected MLA on the other side, he was talking loud and he was not talking decently to me. Another colleague of mine, he got up and asked the MLA on the other side that please speak decently. You are talking to a woman minister. I got up, thanking the colleague of mine, was asking the MLA on the other side to be decent to a woman minister. I don't know where it came from, but all of a sudden I spoke that I do not want any special behavior as a woman minister. You can talk to me and you must talk to me as it comes to you. But if not to regard the other person is your culture, it makes no difference to me. So many a times insults are not given, insults are taken. Why should you take one? God has been benevolent. We are all, I think, who are virtually connected in this program. God has been graceful to us. He has been benevolent to us. We are one of the most privileged children of His. Instead of demanding equality at workplace, we must command equality and respect at our workplaces. And that is what you people have been doing. Why should I ask for respect or equality? My personality, my knowledge, my duty boundedness, my punctuality, it gives me respect on its own. The world is changing very fast. And the Indian wisdom and the Indian ways are acknowledged and all around the world. I have seen that people look upon us and the Indian wisdom to find ways and to find light during the dark moments of life. I would sum up that I feel blessed being a human being. But I feel more blessed being an Indian. But I feel most blessed being a woman. So you have to be yourself. You have to be a person of substance. And we as women have the power to create, we have the power to nurture, and we have the power to transform. I would close or end these words of mine saying that, have you got a little kindness shown? Do you feel God has been kind to you? Have you got a little kindness shown? Pass it on. Have you got a little kindness shown? Pass it on. It was not made for you alone. Pass it on. Let it travel down the years. Let it wipe another's tears until the deed in heaven appears. Pass it on. Thank you.
Thank you so much, ma'am. Thank you for your influential speech. Definitely, we will all enjoy our individuality, not as a man or woman. We should enjoy our individuality of our own personality. Thank you so much, ma'am. We highly blessed with your motivational speech and your gracious presence. Inviting Dr. Premlata Gupta, ma'am, Principal IPS Academy, to give thanks to our chief guest. Dr. Premlata Gupta, ma'am. I think some technical error from madam's side.
Just wait.
Can you hear me?
Yes, ma'am.
Yes, ma'am.
On behalf of IPS Academy, I, Dr. Premlata Gupta, wish to express my gratitude towards Mrs. Archana Chitnis to accept our invitation. Your thought definitely trigger new ideas among all participants, and especially women. You brought new insight of women empowerment among us. I expect your gracious presence in our future events. Again, I mention our deep sense of appreciation for raising daughters. Thank you so much, ma'am.
Thank you once again, ma'am. Thank you.
Thank you so much, ma'am. Now it's time to have a lecture from our eminent speaker, Dr. Sonia Mam from Portugal. Inviting Dr. Vijendra sir to introduce Professor Sonia Mam.
Thank you, Dr. Pratibha Sharma Ma'am, for introducing Professor Sonia Carabinerio. A warm good morning to Professor Sonia Carabinerio. I welcome Professor Sonia Carabinerio. I have a very pleasant duty of introducing our distinguished speaker, Madam Sonia. Professor Sonia Carabinerio graduated in applied chemistry at the New University of Lisbon, Portugal, and obtained her PhD degree in chemical engineering in 2001 at the same university. She was postdoctoral researcher from 2001 to 2003 at the Lisbon University, the Netherlands, and from 2004 to 2007 at the University of Lisbon, Portugal. From 2007 to 2013, she was assistant researcher at the University of Porto, Portugal, and principal researcher from 2013 to 2018. In 2019, she was invited professor in the Wuhan Textile University, China, and integrated researcher at the University of Lisbon. She obtained Hamiltonian in chemistry at the same university. In 2020, she became as a professor at the New University of Lisbon. She is author of more than 20 chapters in books, more than 160 articles in international scientific journals, more than 200 communications to national and international conferences, and more than 15 invited talks. She is co-inventor of one worldwide patent, evaluator of several international conferences, and more than 15 invited talks. She is co-inventor of one worldwide patent, evaluator of several international project proposals, including European Research Council grant. She has more than 4,800 citations and H-index of 39 Web of Science. She is a regular referee of several international journals, being currently one of the top female reviewers in the world. She is also a member of the editorial and reviewer board of several journals. Her research interests deal with catalysts by gold nanoparticles, single and mixed metal oxides, nanostructured carbon material, heterogenation of homogeneous complexes, gas and liquid phase oxidation, and environmental catalysis. Recently, Dr. Sonia has included on a list of the most cited scientists in the world released by Stanford University. So I would like to invite Dr. Sonia for your presentation.
Thank you for the nice introduction, and also thank you for the invitation. I would like to share my screen, but it's saying here that I can't, that it's not activated.
Okay. Kalal sir, please allow to Madam to share her screen.
Okay.
Okay, yes, ma'am.
I can share now, yes.
Okay.
It's saying I can share. Okay, thank you. Thank you very much again for the invitation. And also, it was very nice to hear the wise words of the previous speaker, Mrs. Chitnis. I think I said the name right.
Mrs. Archana Chitnis.
Chitnis.
Okay.
Okay.
Yes.
Sorry, I don't speak your language. Okay, so I hope you can see my screen.
Okay, yes.
Yes, okay. And yes, okay, good. So I'm going to talk a little bit about catalysis by gold, which is one of the key areas in which I work. So as it was said, I am now at the new University of Lisbon, which is called Nova in Portuguese. Nova means new, University of Lisbon. So it's a quite recent university. It started about 50 years ago, and it's already one of the top new universities, recent universities in Europe with less than 50 years. So just for you to see where I am located, let's see here the world map. So here is India, where you are. So here is Europe and Portugal is here, this very small country. So if we enlarge the Portugal map, you see it is here, Portugal is here next to Spain, and here is Lisbon. Here is Lisbon, the capital. So I am from here, from the new University of Lisbon. And this is the University campus. So it's right here, and here it's the Atlantic Ocean. So it's very close to the ocean. It's a very nice campus. So I invite you all to visit if you have the time and the opportunity once the pandemic ends, of course. And so I'm going to talk a little about some properties of gold, because gold is a very interesting metal, which I am very fond of. So, as we all know, gold is yellow and shiny. We all see it. We have seen gold jewelry and gold pieces of art. It's yellow and shiny. It's also naturally occurring. It can be found in nature. In the river, in the old days, people would find little pieces of gold in rivers and streams. Now it's not so easy, but it's still naturally occurring. It's inert in the bulk state, which means that if you have a gold bar, it doesn't react. It stays like that forever. It doesn't get rusty like iron does, for example. It also has these nice properties. It's malleable. Malleable means you can easily squeeze it. So if you have 1 gram of gold, you can beat it so much that you can form a gold foil of 3 square meters. So very, very thin and large gold foil. It's also ductile. Ductile means you can do very thin wires out of it. So the thinnest gold wire you can do is 5 micrometers diameter, which is 10 to 20 times thinner than a human hair. You know, a human hair has about 50 to 100 micrometers diameter. And you can make a gold wire 10 to 20 times thinner than that, because gold is very ductile. It is also very dense. It has a density of 90 cubic centimeters per gram. So if you have a cube of gold with only 37 centimeters size, it would weigh a ton. So it's quite remarkable. Gold also forms alloys. We all know in jewelry, as it is very soft, it's often alloyed with copper, with silver. So the pieces of jewelry we have usually are not only gold, are gold alloyed with some other metal. And is also a good conductor of electricity and heat. Also, gold nanoparticles, they can be found in colloidal solution. So here we have some examples of the white colors they can have. So if we have a solution of red solution, then it means that we have smaller nanoparticles because it has a rather narrow absorption band at 520 nanometers and negligible scattering of light for lower sizes. So we see here a TEM image of small gold nanoparticles that have this red solution. But if we have blue or purple solutions, then it means that we have larger nanoparticles, which means that the absorption band shifts to longer wavelengths and light scattering becomes marked for larger sizes. So here we have an image of larger nanoparticles that are blue in solution. And the main issue in working with gold in catalysis is that gold is only active in the form of nanoparticles well dispersed on the support. So as I said before, gold is not active in the bulk state. If you have a gold bar, it doesn't react. So it needs to be in the form of nanoparticles. So there are crucial factors affecting the activity of gold nanoparticles, which are the nanoparticle size. The smaller the size of the nanoparticles, the better, the most active the catalyst will be. Also, the reducibility of the support is very important, and also the interaction of the support with gold. We will talk about that later. So, the impregnation method, which is often used for other metals like platinum and palladium, it's not suitable to prepare gold catalysts because it gives too large inactive gold nanoparticles. And an example is here. See, you see a very large gold nanoparticle of almost 400 nanometers. It's not a gold, it's not a nanoparticle, it's a nanostone, very big. And we know that the presence of chloride causes sinterization of gold nanoparticles, especially at high temperatures. So it makes them inactive. Therefore, the removal of chloride is very, very important. Some efficient gold methods are, for example, Sol immobilization or the colloidal method, in which the gold precursor, in this case, hydrochloroauric acid, HAUCl4, is reduced by a reducing agent, which can be citric acid, can be sodium borohydride, or any other, in the presence of an excess of stabilizing caping agents, ligands, or surfactants, which can be several ones, before addition of the support. And the addition of these agents prevents the gold nanoparticles from getting together. It spreads them, keeps them away from each other, shall we say. And there is also deposition precipitation, in which the pH of a gold precursor solution is raised until usually 9, but can be 9, 10, with sodium hydroxide or urea before addition of the support. What this does is this makes the hydroxylation of the gold ions, so it also removes the chloride. It's removed in the washing. There is also co-precipitation, in which the solution of the precursor and water-soluble metal salts, for example, nitrates, are poured into an alkaline solution, which can be one of these, sodium carbonate or ammonia, and with stirring. So the hydroxides, the two hydroxides or hydrated oxides, are precipitated simultaneously, both the gold and the metal oxide. So it's called co-precipitation, simultaneous precipitation. And there is also photochemical deposition, in which the gold precursor is dissolved in water and methanol, and it's mixed with the support. It's sonicated, photodeposited using a UV lamp. So here we have this solution before. This is with titanium dioxide. So it's white, totally white. We cannot see anything. But then as we turn the UV lamp on, so there you see it, the lamp on. So afterwards, we put it in the dark. This was just to take the photo, but this photochemical deposition takes place in the dark. And then there is a simultaneous reduction of the metal ions by the conduction band electrons. And it can be enhanced by the addition of the so-called sacrificial electron donors, like methanol, for example, that can supply an almost unlimited amount of electrons and then increase the rate of photodeposition. So afterwards, you see that the solution has this nice purple color, which means that photodeposition took place. So it's the color of gold nanoparticles. So you see before and after. And there is also a method, ultrasonication, that was discovered by chance. It's similar to photodeposition, but without the photodeposition itself. It's just the sample is sonicated for 8 hours. This happened because we just forgot the solutions in the sonicator, and it stayed there for 8 hours, and we did not put it photodepositing. And what happened is that after those 8 hours, it was very nice and purple. So we decided to test that sample, and it gave very good results. We are going to talk about that later on. Other efficient gold deposition methods, for example, liquid phase reductive deposition, in which the gold precursor is mixed with a solution of sodium hydroxide and aged for 24 hours in the dark before it is impregnated in the support, or double impregnation with the gold support and another step of impregnation with the solution of sodium carbonate. So here we have an example. This is, here you can see gold nanoparticles deposited on zinc oxide. So here it's the average size of particles was 2.9, and the size range is from 1 to 12, more or less, or 13. So the size of the nanoparticles that we found. And now we're going to talk a little bit about the gold prices. So this can be a problem. When gold research started, well, the increase of gold research started some years ago, but in 2005, more or less, when I started to be interested in this subject, gold was significantly cheaper than most traditional platinum group catalysts. So if you see here, in June 2005, those were the gold prices. Gold was, compared with other metals, gold was 12 euros per gram, which was significantly cheaper than platinum, that was 26 euros per gram, and rhodium, that was 60 euros per gram, but a bit more expensive than palladium, that was 7 euros per gram. Okay, since then, since the year 2000, more or less, so we were here, 2005, more or less, and since then the prices of gold have been rising up to this maximum here, then decreased a little, and now they are rising again. So the current prices compared to other metals is gold has now a price larger than platinum, more or less similar than palladium. Well, palladium is a bit more expensive. Gold is now 49 euros. It's larger than platinum, that is 31. The palladium is a bit more expensive, 61, but much lower than rhodium. Rhodium is now 500 euros per gram, which is a lot. So if you see, it's quite interesting that palladium increased a lot in these last years, and rhodium, of course. Platinum, see, it's more or less the same. 26.31, platinum is quite constant, and gold raised, but not as much as the others. So those are the current prices of this month. I was checking. So with these prices much higher than before, at least higher than platinum, we ask, is there a golden future for gold catalysts? Well, I think there is, and I'm going to tell you why I think so. Well, gold has advantages over other metals. For example, on CO oxidation. CO oxidation is one of the simplest reactions occurring. That is a CO plus oxygen to give CO2. So gold is active already between -70 to 70 degrees Celsius, which is quite interesting. So you can do this reaction on Antarctica, on the North Pole, because this is room temperature there. So this is very, very low temperature. While platinum group metals, they are only active above 100 degrees Celsius. So you have to heat with platinum gold metals. With gold, you do not need to heat. You can use room temperature even in the North Pole. It's quite interesting. And there is also the water gas shift reaction, which is the CO oxidation, but in the presence of water. It gives CO2 and produces hydrogen. So we have here a gold catalyst to compare with the copper and the platinum catalyst. And we see that gold is already active at 100 degrees Celsius, while other catalysts are only active at much higher temperatures. And it's important, this reaction, it's important to produce hydrogen for fuel cells. It would be nice if the person that has the microphone on can switch it off, because otherwise other people cannot hear my presentation.
Mute all, sir.
I hope you can still hear me. Well, the hydrogen generated for a carbon, it's impossible. I think you cannot hear me with this noise.
Hello, Dr. Bhagwan. Just 1 minute, ma'am. Please interrupt me.
Okay.
I request to all the participants, please mute your microphone, please. You are disturbing. Hello. I request to all the participants, please.
Okay, good.
Okay, yeah, thank you, ma'am. Please start.
Okay, thank you. Thank you. Because otherwise other people could not hear.
Yes, yes.
I was screaming and you could not hear anyway. So the hydrogen generated for a carbon-containing source, like methane, for example, we have these reactions. So we have methane with reaction with water. It generates CO2, and it also generates a little bit of CO. So the generation of CO2 is not the problem for fuel cells, because we want to produce hydrogen for fuel cells. So CO2 does not affect, at least the proton exchange membrane fuel cells. It's not a problem. However, there is also the production of CO, this secondary reaction, and it's only 0.5% CO that is being produced. And you might say, well, 0.5% is not much. It should not be a problem. But in fact, unfortunately, it is, because above 0.01% CO in the stream is enough to poison the platinum proton exchange membrane fuel cells. So we have to get rid of this CO. And what happens is that gold does this oxidation reaction, as we saw, so oxidizes CO very easily and very spontaneously, shall we say. So it's quite good. However, platinum does the same. Platinum also oxidizes CO very well. But the problem is that platinum is also a very good catalyst to oxidize everything. So it also oxidizes the precious hydrogen that we want to form. And this is bad, of course, because we want to get hydrogen, and the hydrogen is being removed by platinum. And a good thing about gold is that it selectively oxidizes CO. It doesn't oxidize hydrogen. So gold is much more selective than platinum and other platinum group metals in the oxidation of CO in the presence of hydrogen, which is called the preferential oxidation reaction, or PROX. And also, gold has other advantages, as it is nearly insensitive to CO2, this CO2 formed here, and its activity is even enhanced by water. So, gold catalysts are good candidates for hydrogen production and purification in these water systems, which is quite nice. And there are many other reactions efficiently catalyzed by gold. So we have complete oxidation of hydrocarbons, decomposition of volatile organic compounds, oxidation of alcohols, sugars, hydrogen peroxide synthesis, hydrogenations of many compounds like aldehydes, ketones, hydrocarbons, ozone decomposition, SO2 removal or reduction, reduction of nitrogen oxides with propane CO, hydrogen, homogeneous catalysis, autocatalysis, automotive catalysis, sensors, many others. I've worked with some of these reactions, and I'm going to give some examples only. It's not possible to talk about everything. It's a lot of reactions, a lot of work. So let's talk a little about the CO oxidation reaction, which is a simple and intensively studied reaction, but not fully understood. And it has a very large importance in pollution control, air purification devices for indoor space like gas masks, cleaning of automotive exhaust gases, fuel cells, gas sensing, etc. And gold catalysts have advantages in this reaction, which come from their improved activity at low temperatures that we already talked, and stability in the presence of water. So we have here CO oxidation on platinum. It follows a Langmuir-Isherwood model, very simple, which is the CO is adsorbed on the catalyst. The oxygen is dissociatively adsorbed. So O2 divides in oxygen and both oxygen atoms adsorb. And then the CO and oxygen adsorbed react together, form CO2, and this CO2 adsorbed is released as CO2 in the gas phase. Very simple, very nice. Okay. However, the CO oxidation on gold is not that simple. And it follows the so-called Bond and Thompson mechanism that was proposed by these authors in 2000 and later confirmed in 2009, which is similar to the Mars-Van Crevelen mechanism. So what it says is that the CO is not oxidized by the oxygen that is being supplied in the reaction media. It's the oxygen from the support, from the oxide support, that is migrating to the surface and reacting with the CO and producing CO2. So the oxygen that is being supplied in the stream is only used to replenish the surface. And this has been confirmed by experiments done with marked oxygen. And then it was seen that the first CO2 that was formed was not marked because it was from the oxide support. Only afterwards, the oxygen marked was replenishing the surface, and then the reaction was continuing. And indeed, we also did some experiments without CO in the, only with CO in the stream, without oxygen. And then we saw that CO2 was still formed up to a certain extent, and then it would decrease because all the oxygen from the support would be totally gone, of course. So we have here some example of gold on metal oxides. So here on copper and on lanthanum oxides, prepared by this double impregnation method and by the liquid phase reductive deposition. So we see here the size ranges and the average sizes. So these catalysts were tested on CO oxidation. So here we have only at room temperature to compare, and we see that this dim method was very much better than this liquid phase method, and compared to similar catalysts, gold on the same oxides from literature, it was quite larger. And here, if we see all the temperatures, here we see at 25 degrees that the conversion was much higher for this dim method than with the other methods and then at other temperatures. You might say, oh, didn't you say that the reaction was, that it was already active at lower temperatures and so on and so on? Yes, indeed. But here we are using 5% CO, which is quite large. If you see in literature, usually authors use 1% or even less CO. But so we did a very large amount of CO just to test these catalysts, and indeed here the activity was quite nice. So also an example of gold on zinc oxide. This is a zinc oxide prepared by chemical vapor deposition. So it gives these nice needles of zinc oxide. And we have here the gold nanoparticles deposited. So it's by the double impregnation method, photodeposition, and the ultrasonication method. So if we look at the sizes of gold nanoparticles, we see that this is the lowest size, the double impregnation method, the lowest size, much lower than those ones. So if only the gold size was important, we would expect that this sample was the most active, right? But then, as we obtained the results, we saw that this dim method was okay. It was better than the photodeposition. However, this ultrasonication method was much better. So this is for zinc CVD, chemical vapor deposition, and this is samples, gold on zinc samples, commercial ones from Strem Chemicals and from Evonik. So this CVD zinc made in a lab was much better than the other ones, and this US ultrasonication method was also much better. So if you remember, this ultrasonication method was that sample that was forgotten there for 8 hours in an ultrasonicator. And so it gave this very nice activity. So we did not know why. And you see here, indeed, it's much better on all temperatures than the photodeposition and zinc itself. So you see the zinc oxide itself without gold, see, it's very inactive. Only at 400 it starts to convert something. But with gold, it's much, much better, of course, as expected. So we did a detailed investigation on this sample to see what was going on here. It was not the gold size, it was not the interaction of, it was not the support, because it was the same support. So something had to be happening. So what we found was that the gold nanoparticles were epitaxially grown on the zinc oxide support in some cases. So if we do a fast Fourier transformation here, we see those, we get this diffraction pattern, these spots. And if we identify these spots, we see that those ones here, the circles, are gold and the stars are zinc oxide. So what we found is that there were some crystallographic relationships found. So parallel directions of gold, of some planes of gold and planes of zinc, and parallel planes of zinc oxide, I mean. And some relations, we did a few degrees for these planes. So we see here that they are epitaxially grown, so a bit aligned here. And so this epitaxial growth of gold nanoparticles on zinc oxide and those strong metal support interactions, they may result in improvement of the catalytic properties of this sample. because no epitaxy was found for other samples. And indeed, so this was our justification and what we said on the Journal of Catalysis paper. So we also have iron oxide supports. This is commercial iron oxide, and this is nanostructured iron oxide obtained by calcination of iron nitrate, obtained in lab. So you see it's much nicer one because it has those nice planes, while it's nanostructure, while the commercial one from all this is quite large nanoparticles. And so once we deposit gold on these supports, so on commercial iron, we have this size range from 6 to 30 nanometers. And on nanostructured iron, see, we have a lower size range, 1 to 7 nanometers. And indeed, if we do the CO oxidation, we see that DIM is much more active than this, than the other methods. So, and compared to the whole gold console catalyst, which is a reference gold catalyst, so we see that it's much better. Our samples were much better, had much higher activity, especially those ones. So here you see the influence of commercial or nanostructured. On the nanostructured, we'd get lower gold nanoparticles, which have higher activity, much higher activity than the gold deposited on the commercial support. And we have here an example of gold undocked cryptomelane. So cryptomelane is an octahedral molecular sieve. So it has this formula, and we have these straws, looks like straws of cryptomelane, and we see those nanoparticles. We could think this is gold, but no, actually this is cerium oxide deposited here. So we don't see the gold. For us to see the gold, we have to use this diffraction technique that gives this contrast. So here we can see the gold, and we can identify it by ADS. And here, if you see the catalytic activity, there's something interesting, is that here we have the cryptomelane alone and cryptomelane with gold. So we add gold to cryptomelane and nothing happens. The activity is exactly the same. The curves are almost the same. If we add cerium to the cryptomelane, it gets worse. It goes at much higher temperatures to have conversion. However, if we add gold to the cerium doped cryptomelane, we have a much better activity. So how come? Let's try to see why. So we thought we could think, okay, then it's the cerium that is the catalyst. So let's put gold on cerium oxide. And so we put the gold on cerium oxide, and we saw, see, gold on cerium oxide is not as active as gold on cerium doped cryptomelane. And gold on cryptomelane itself is not active at all, at least until this temperature, more or less. We are seeing just this part here. So what is happening? We saw that gold on cryptomelane had very large nanoparticles. That's why it was inactive. So it was only a waste of gold because it's the same. Gold on cerium had very low nanoparticles, so it should be active. It is indeed, but here, gold on cerium doped cryptomelane has larger nanoparticles, but it's more active. So why? So we found out, and it was published on this paper, that cerium increases the number of defect sizes that anchor the gold nanoparticles. And the cerium nanoparticles also enhance the charge transfer between gold and cryptomelane. So that's why the higher activity. So let's leave behind CO oxidation. I could give much more examples. I have tested other catalysts, but we cannot talk about everything. in one day. So let's talk about the activity of gold for oxidation of volatile organic compounds, which are compounds that are emitted from a wide range of industrial processes and transportation activities, so from industries, and they contribute to air pollution. They are toxic, malodorant, and smoke formation. So we see here examples from where box come from automobiles, from these solvents, from those inks, from those factories. So very bad. So some examples of VOCs which we studied are ethanol, toluene, and ethyl acetate. So we studied the oxidation of these three VOCs to compare. And so the thermal oxidation of VOCs needs to operate at very high temperatures. If we want to oxidize those VOCs, to destroy them, we need to go up to 700 degrees Celsius, 700 to 1000, which is a lot. And this leads to the production of nitrogen oxides because they react with the nitrogen of air because of the very high temperatures. Therefore, if we have catalytic oxidation, if we add a catalyst, the catalyst can decrease this temperature to starting at 200 and something degrees Celsius. So the NOx production is much lower and also less energy is needed. So a Mars van Crevelen type of mechanism occurs, which is like this. We have the oxygen, the oxide, the surface oxide, and then the VOC comes. So the VOC is connected to the oxide. The products are released and there is an oxygen vacancy here, which is replenished by the oxygen on the restores and the cycle can go on. So what is the role of gold here? The role of gold is to enhance the reducibility and reactivity of the surface of the oxide and also increase the exchange rate between lattice and surface oxygen. So it is a good catalyst, and we are going to see examples now. So for example here, oxidation of ethyl acetate. We have here on these white symbols, we have here ceria, only ceria, two types of cerium oxide. And we see here it's 100% conversion. And see that it's not able, ceria alone is not able to achieve full conversion of the VOC. And if we add gold to the ceria, we see the curves here that the full conversion is achieved at much lower temperatures. So we see here this temperature was 100, 300 something, and here we have at 200 and something. If we see the oxidation of ethanol, the difference is even larger. You see here only at 300 and something, and here already at around 200. We have full conversion because here conversion was not full, so we don't reach 100%. And we have here also oxidation of toluene. Toluene is the most difficult VOC to oxidize. It's very hard to oxidize this molecule. So you see here, at 400, we don't reach full conversion. And if we add gold, we have full conversion at 200 and something. So it's quite good. And if you see here, manganese oxide, oxidation of ethyl acetate, an example. So at 200, it's the best catalysts here. At 200, we get already oxidation, and here we put full conversion and oxidation, and here we had to wait until 400, and it was not full conversion. So if we look at the gold nanoparticle sizes, those ones were around 5 to 12, and this one here was lower. See, we see the gold size was lower here, so the gold on manganese oxide was a better catalyst. So we have here also some other examples. See, yttrium oxide is not a good catalyst at all. At 400 degrees, we only have about 40% conversion. And if we add gold, we have at much lower temperature full conversion. Also here with toluene. Toluene is the most difficult rock to oxidize. As I said, see, almost nothing, almost no oxidation. And with gold, we get very good oxidation. And other examples, ethyl acetate and toluene with manganese oxide. See, almost nothing. With gold, see, at 400, it was only 70. And here at 200 and something, we get full conversion. And also this one, almost nothing. And with gold, we have much better result. So quite interesting. The sizes, see, they are about 5 nanometers, all of them, more or less. And so other example, so nitrous oxide, N2O, which is a gas that for a long time it was considered as non-pollutant, but in fact it is a harmful gas. And because it has a powerful greenhouse effect with global warming, 300 times higher than CO2, which is remarkable. Lucky us that this is only 4% in the greenhouse gases. It's only 4%, this one, while CO2, it's 60%, the composition of the pollutant gases in the greenhouse gases in the atmosphere. But this gas has a much larger potential as greenhouse gas than CO2, so it's quite dangerous. And its problem, it has a long lifetime in the atmosphere, about 150 years, which is a lot, really a lot. And it has been increasing its amount. And if you see here, the greenhouse gases, they exist naturally, of course, but there is the solar radiation, and if this layer is not too much layer, you know, it can escape the heat. But if this greenhouse effect is intensified by human activity, then less heat can escape into space, so there is the global warming, which is bad. So this ozone layer depletion potential is similar to that of chlorofluorocarbons. In the past 200 years, 50% increase, and its dissociation only occurs at very high temperature. So the direct decomposition of this gas has advantages, as it would be more efficient, simple, etc. So we use metal oxides loaded with gold. So we have here some examples of TEM images, and here the gold nanoparticle sizes obtained. They are right here. So these ones were the lowest sizes. And then if we do a hydrogen temperature programmed reduction of these catalysts, we see that gold on alumina, almost no reduction. We see almost no reduction. If we see gold on zinc oxide, we see no reduction on almost. So these peaks are only dehydroxylation. So this is the thermal conductivity detector signals. So almost nothing. And if we see the gold on titanium dioxide, also almost nothing. And we see a peak here on gold, but this is the reduction of gold. So not of the oxide. If we see the gold, the serum oxide with and without gold, so without gold, we see a reduction peak here and another one here. So this is the surface oxygen reduction, and this is the bulk oxygen. If we add gold, what happens? The surface oxygen is reduced at much lower temperatures. So you see the reduction activity increases a lot by addition of gold, and the bulk oxygen remains the same. If we see the gold on iron oxide, so here, this first peak is this reduction of Fe2O3 to Fe3O4, and this is from Fe3O4 to FeO, and this one is to iron metal, this at higher temperatures. If we add gold, these peaks shift to lower temperatures, so reduction is enhanced. It's quite good. So if we look at here, we see that the most reducible oxide is iron, because see the scale. Here this peaks, but the scale is very low. See, the scale is very low. And this scale here of iron is much higher than this one. So this is the most reducible oxide, iron, followed by cerium oxide. So keep this in mind for us to interpret the following results. So we see here N2O conversion using gold catalyst. So here we have the results. So what happens here? If we look at the oxides alone without gold, which are the white symbols, what we see is this catalytic performance order. Iron oxide, followed by cerium oxide, followed by the other oxides. So if you remember, this one was the most reducible one, wasn't it? Followed by this one. So if we add gold, we see exactly the same trend. We see here that gold on iron is here, followed by gold on cerium, followed by gold on the other one. So the addition of gold increases the catalytic activity. Of course, it's these dark symbols are higher. Of course, the curves are higher, but the order is maintained. The order is the order of the reducibility of the supports. So the activity is not related with gold nanoparticle size, because if you see, these sizes are similar, 2.3, 2.4, but this one is much better. See, one is here and the other one is here, much higher. This one is not the gold nanoparticle size. It's the reducibility of the support that is playing a key factor. See, it's quite interesting what we found. Also, if we look at the last reaction that we are going to see today, at CO2, which is the most significant long-lived greenhouse gas in Earth's atmosphere, it's this CO2. We see that its concentration keeps increasing, unfortunately. So in the pre-industrial times, it was 280 ppm. We have 400 nowadays, and by the end of century, it can be this higher unless appropriate mitigating actions are implemented. So we don't want this earth, this desert earth, we want this nice green, blue earth. So we need to reduce the rate of CO2 emissions, capture and store anthropogenic CO2, and use atmospheric and industrial CO2 to produce useful chemicals and fuels. So we did CO2 hydrogenation using gold on metal oxides. So we got these results, so let's analyze them. So we see here that zinc oxide, look, it's the only oxide able to produce methanol. So we wanted to produce methanol, but sometimes we obtain CO or methane. So methanol is only obtained here if we see the oxides without gold. And we see that gold on aluminum is the worst catalyst because it's the lowest, you see the lowest amounts. And gold on cerium, see gold on cerium, it's the most active catalyst, in fact. So it's also a reducible oxide, and it was better than this one of iron. If you see it, I mean, it was better for methanol, to obtain methanol. But if we want to obtain CO, see, it was much better than gold on iron oxide. But it was a very active catalyst, and it was stable. See, it was very stable up to 48 hours. So we see here, we kept it running for 48 hours. So the CO2 consumption was stable, and the methanol formation was also stable. So it's quite good and stable catalyst. It was quite nice. So finally, some conclusions. You are all tired of listening to me. So these were just examples. I studied many other reactions like oxidation of alkanes, oxidation of alcohols, heterogenization of gold complexes, other metals, but of course cannot talk about all of that in one day, so perhaps some other time. But for now, the conclusions from these studies I showed today show that gold is a good catalyst for several different types of reactions. It has unique features and advantages over other metals. However, it is only active in the form of small nanoparticles, well dispersed on the support. The smaller, the better. We already saw that. We also saw that the small nanoparticle size of gold, although extremely important, is not able to explain everything, as catalytic activity also depends on the nature of the support and on the interaction of the support with gold. We saw that different supports gave different activities, and also the interactions, like the case of the epitaxial growth of gold nanoparticles was very important. So my final conclusion is that gold catalysts have a golden future. So some acknowledgements for funding, and I invite you all to visit Portugal, and I show you some nice images of Lisbon, where I come from, and of near Lisbon, this nice Caparica beach, where the university, very close to the university, if you remember the air view that I show you of the campus, it was near the Atlantic Ocean, very nice, and those nice monuments of Lisbon, and here near Lisbon. So once the pandemic is over, you are all welcome to visit Portugal and Lisbon. So thank you for your attention.
Thank you very much, Madam Sonia. Hello.
Hello. Yes.
Okay. Thank you very much. Yes. Thank you very much, Madam Sonia, for sharing your deep knowledge about the gold nanomaterials as catalysts and properties of gold nanomaterials and its comparison with other catalysts. So thank you very much. It will be a great pleasure for us to listen to you again in our future events. Again, thank you very much, Madam Sonia.
Thank you. Thank you so much, ma'am. Thank you. Thank you so much for joining us. On behalf of Department of Chemistry, I extremely give my remarkable acknowledgement to you, ma'am. Thank you so much for joining us, and you make our event a grand success. Thank you so much. And your lecture was extremely nice. It was appreciated by all departments. Actually, one of our faculty members says it is very important for us. So interdisciplinary point of view, everyone has joined it. Thank you so much once again for joining.
Thank you for the invitation.
Thank you. Now it's time to conclude the event by wishing that each one of you will cherish it for a long time. It is my privilege to propose a vote of thanks. First of all, I would like to propose hearty vote of thanks to our chief guest, Mrs. Archana Chitnis, for gracing today's international webinar and for taking out time from her busy schedule and enlightening us with the knowledge. Thank you so much. I am sure that all the participants have taken note of your suggestions and will be discussing within their organizations the action to be initiated at their level. With this word, I would like to thank our eminent speaker, Professor Sonia Carabinerio, for making excellent presentation and making this international webinar interesting and meaningful. Once again, I would like to thank Professor Sonia Carabinerio for giving their precious time. Thank you so much. Also, I would like to extend a special thanks to our President, Architect Achal Chaudhary sir. You always motivate us to organize such events successfully. I also wish to express my gratitude to our Principal, Professor Premlata Gupta, for providing encouragement and support and for giving permission to organizing this webinar. Also, I would like to extend a special thank to Indian Association of Chemistry Teachers and its present President and my guide, Professor Brajesh Pare, for the collaboration with us and promoting of GWB 2021 in India. I acknowledge the unwavering support received from the HODs of all departments, faculty and staff members of our department. My special thanks to technical team of our department for smooth execution of webinar at digital platform. I must mention a deep sense of appreciation for their valuable contribution to the organizing the event. Last but not least, I thank all the national and international participants for their active participation in this event. I once again thank you everyone for making this program successful. Now I request to all the participants, please stand at your place for the National Anthem. Thank you.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय जय जय जय हे
Okay, thank you all the participants again, and thank you Sonia Mam.
Thank you everyone.
Thank you.
Thanks all participants to joining. Thank you so much.
Okay.